Can you hear me? Okay, so we can get started. So I did a pass over all the slides up to now. I think the only one I didn't manage to clean up yet is the one of today. And they should be, I think Andy should have uploaded it on Stellar. So check them out. They should be all a bit updated. I'm very good at putting typos in the slides. So if you find some, please let me know so that I can fix them. I'm also trying to turn them into new set of notes. I thought I was going to do all of them. I did half of them. So I'm going to try to do a few more and then hopefully give it to you as a present. Because this is my last class, so from next class you finally start to do real theory with Sasha. But today we do a last little bit of hacks and tricks, talking about neural networks, and for real. It's not just about another class like last time. Today we really talk about neural networks. So I think the good thing about neural networks is that they're a super popular topic. There are tons of things that are going on, but it's also very easy to do one class on the things that are pretty stable because there are not so many. We're still in the process of understanding how they work, and their usage has not a lot of guidelines. So we're going to try to stick to the basic facts. So here it's going to be a relatively simple class where you just try to list what they are, why you might care, how they relate to what we did before, and why the hell are they called neural networks anyway. We can take many point of views. The point of views we're going to take is some of the following up the discussion we started last class, that is discussing our data representation. If you remember the story there, it was in half of the course, we have discussed what you do when you have supervised data and you want to learn W given phi, and then the question is typically, okay, but how do you get phi? And we basically just provide the mathematical tools to define phis based on some kind of expert knowledge. And last class we start to ask, can you learn phi? Okay. The first thing we did was to consider the case where the kind of data you have are unsupervised. Okay, so you have the inputs but not the outputs, and then immediately you have to say, okay, but if I don't have the labels, what is my objective? What is my loss function? And we discussed a couple of different ideas, but the main one we discussed was the idea that you would like to say that for at least the point in the training set, this is a good proxy for xi. Okay, say something like this. Unfortunately, phi here, remember, is a map that sends the data space into some kind of feature space, and so this doesn't make any sense. Okay, I cannot compare the representation with data directly. So if I want to go in this direction, what I could do is to actually introduce the reconstruction map, which is somewhat the dual of this map. The reconstruction map is a map that goes from the feature space back to the original space. And now I can make sense of this. These all live in the same space. I can now take the distance between the point and the reconstruction. I can now consider the average error. And minimize over both psi and phi, okay? And we commented sometimes the pair phi psi is called the autoencoder. Okay, so that's roughly speaking a summary of the first part of, or I guess 1/3 of last class, which was basically introducing this and making sense of this one expression here. And then what we did in the rest of the class is just noticing how this framework, this framework is super general, right? These two can be anything. First of all, we observed that this doesn't make sense because if we can resolve the identity, this problem becomes trivial. And second, we start to discuss a class of constraints. Specifically, we consider the case where psi is linear and phi x is of the form this form, okay, which we call AJ if we call AJ the columns of this matrix, you can think of them as a dictionary, a set of atoms, and then you can view this as just a linear combination. So this is basically saying, provided a dictionary, find me the best coefficient that gives me the best linear combination, okay, to reconstruct X. This is what we call a nearest neighbor encoding, okay? And this is not a restriction yet, but it becomes a restriction when we make specific choices of what kind of linear function and what kind of set of coefficients. But already with this, we can now specialize the expression above to write down separately the minimization over phi m psi. Okay, and so what we discussed is the moment you make that assumption, you go here, what you obtain is essentially what you might call dictionary learning, which is a particular example of autoencoders where the reconstruction is linear and the representation is non-linear, but is given by a nearest neighbor encoding. Okay, so again, this one is linear, but this one need not be. Think of, for example, the example we spent the rest of the class last time to make example. We discussed PCA, sparse coding, k-means, and for example, in k-means, you just take an assignment map. It's not just a simple linear operation. You have to take a max. Okay. And we left last class, okay, observing the connection with this, with other form of autoencoder, and with matrix factorization, which is typically linear. What we want to go back today is the very first point. This is the one where we restrain ourselves to just consider unsupervised data. Okay, the main motivation was the idea that we would hope to learn could use unlabeled data to try to get a good representation that reduce the need of labeled data. Okay, and I think this is one possible way to go. There are possibilities to start to look at supervised data. Okay, and so essentially the question is quite similar, but we say, okay, I want to learn phi. And I am given a supervised set. Okay? Now, how do I learn phi? Now, in that approach, we introduced the reconstruction. We can map because we didn't have a way to somewhat express the quality of a representation if not going back to reconstruction or distances, but it's kind of the same thing. Okay? But here we have data, so we can now try to see if do we need the reconstruction to design a loss function, or we can just do something we know? And of course, the answer is no. What could we do? Well, we could say, let me try to do in the same style as before. I have now my function. Very much like we did in the rest of the course, we can define the loss function of the model. We can consider the empirical risk, and we can now do the empirical risk minimization, where we simultaneously optimize not only over W, but also over phi. Phi. Okay? That's okay. I mean, it's allowed. We have data. Why don't we do that? Okay? Again, the main difference is unsupervised, supervised. Now, as with this line, we are at the level of abstraction of this line, right? It's not a very manageable assumption. What do we do with that? What is phi? How do we learn it? To be able to learn phi, we have to do something like we did here, which is parameterize our phi in some way. That's what we did with W in the first place, right? Or if you want, the point here is that we had our F. We didn't know how to parameterize it. We didn't know how to learn it because we don't understand. We have to explain to the computer what an F is. And so we started by considering a linear function. And then we sweat to try to make it nonlinear. So if now you want to learn not only W, but also phi, what can you do? What is the most obvious parameterization? Well, presumably still linear. You can just assume that this is a linear map. okay? So what we want to do is to assume it's linear. It takes us 5 seconds to check that this doesn't get us very far. It actually gets us somewhat in trouble without obvious gain. And then we try to make it more nonlinear, okay? So example 1 is, let's consider phi to be linear. Notice that reconstruction is not in the picture anymore, okay? There's no need for that. At least in this perspective, it's just not needed. If linear, essentially it means that we can identify this with a matrix, okay? P by D, okay? So the action, in this case, what we have is that we just get this problem. I'll just use, well, whatever, doesn't matter. Okay, where I'm simultaneously, so I just replaced phi of x. Sorry, and I'm also changing there. Let's assume the loss are symmetric, so I don't have to sweat to remember the order. I simply replace phi with w, wx, phi x with wx, okay? And now this problem is solvable, okay? In the sense that now it becomes a multivariate problem on some finite dimensional space. I can go on and try to solve it, okay? We can make a couple observations, though, on this model. The first one is that it is non-convex. Again, you can check quickly. Oh, I guess it's kind of obvious, but fixed W, it is convex in fixed capital W, it is convex of lowercase w, because it's what we've been doing for a month and a half. Fixed lowercase w, it is also convex in W, and you can check this in a bunch of different ways. In fact, it is even linear in W in this case, capital W. The point is that jointly is not convex. Okay, so in general, you are dealing with a non-convex problem, and in general, convergence of any gradient technique will be extremely hard to prove. Okay, because you can get stuck in critical points that are not global minima, or maybe not even minima at all. Okay, they are saddle points or even maxima. Now, interestingly enough, if you start to make some assumption on the data matrix and the size of P and D, the dimension of the data, basically how many points you have, how many dimensions they live in, and the number of parameters you use in this model, there is this idea that over-parameterization helps. And so there is a bunch of results that shows that indeed this problem is not as hard as it might seem. Okay, there is some kind of redundancy. And I think if you just look at the one-dimensional case, it gives you a sense of what it might mean. Okay, there is some blessing of over-parameterization happening. We're not going to go in that direction, which is a bit more theory, proving that this is not so bad. What we want to notice instead is that, okay, maybe it's not so bad, but it certainly is more complicated than before. And on the other hand, from a modeling point of view, it's not really obvious that we gain much at this point, because the function we are considering is basically still linear. You can pull this on the other side, you get V transpose Wx, you can call this beta, and now you have B transpose X. Okay, so the model we're considering is still linear. So if we're shooting for building a nonlinear model, we fell short. Okay, of course now if you consider to putting constraints on the different of the lower case and capital case W, you can get some flexibility that maybe you didn't have before. For example, here I can just put different norms of B on B, but here I can try to make now more complicated norms on both capital W and lowercase w. I could take the trace class, the trace norm of W, and the L1 norm of the lowercase w. Okay, so it does give me some flexibility, but still we are dealing with linear functions. So the question is, can we learn nonlinear functions? Can we learn nonlinear representation that will lead to nonlinear functions? Okay. Now, if you think about that, essentially the point is that we need, at this point, we need something which is more general than linear function, but is still parameterizable in some way, okay? Because we need, in the end, to try to estimate the parameter that correspond to W. So this is not okay. So this phi is not okay, or it's fine, but it's just linear. We have to make it non-linear. How can we make it non-linear? Well, essentially, as we discussed at the beginning, we have a couple of different ways. One way is to put a non-linearity in front of x. Okay? Say, okay, I'm going to do this. Put a lowercase, not to confuse with the other one. And this will be putting a feature map chosen by Tommy or Sasha that are very good at choosing feature map. Then you can do kernels and stuff like that, okay? But then you're still not doing very far, because once you put the W transpose here, then this is the same as beta transpose phi of x, okay? Again, this phi is the one that you fixed a priori. So in some sense, you said, I wanted to learn the representation, but I'm not really doing it. I'm just keep on doing what I was doing before. Okay, that's kind of what you're doing here. Make sense? So again, this phi is not this guy. Okay, this is a bit, maybe let's call it like this. It will make it more. Is a feature map. Okay, fixed a priori that I'm not trying to learn. Polynomials, kernels, you name it, one that you like. Okay, so if this one is ruled out, there are not a lot of other places we can put the non-linearity, right? So where shall we put it? Here. Because literally there are not a lot of other places we can put it, okay? And at this point we get this function. It looks like this, okay? Where sigma is some map that goes from Rp to Rp, and it has to be nonlinear, because as a y, again, we go back to something simple. Okay? Okay, this is almost a neural network. Almost, because a neural network is a special case of this, where you actually assume the nonlinearity to be pointwise. So you assume that sigma for some vector a is equal to sigma a1 sigma a p, where sigma is some function from R to R. Okay, it's a linear, is a one-dimensional function, and let's make this assumption. Okay, okay, this is an assumption. Okay. Then in this specific case, we can now rewrite this function f of x where these are the columns of W, okay? So I just rewrote this, okay? This is an inner product. Is the inner product of the rows of this times this guy, and I have D of them, okay? Sorry, P of them, as many as the rows. So one row, one inner product, and there are P rows, okay? And then each one is weighted with one entry of this vector, and that's what it is, okay? Now that's a neural network. So what we want to do, yes, is the dimension of the feature. So we haven't introduced the jargon of neural networks yet. So for us, it's just the dimension of the feature space. Okay. So in the language that we kept so far, we had a feature map with a certain dimension in the feature space, that representation space, and that's P. D is the dimension of the input. P is the dimension of the data. In a second, there's going to become the size of the number of the hidden units. Okay. Questions? So what did we do so far is just we open the box. We start to look at the question of how do you learn phi. We spend one class looking at unsupervised approaches based on the dictionary learning approach, which is based on a nonlinear reconstruction, a linear representation. And today we move back to supervised learning. We throw away the idea of reconstruction. We just go back to the objective that we like, which is prediction in terms of a given loss function. And we just ourselves how to parameterize a representation in order to be able to estimate it from data. Okay? And we find out that if we don't want to do something linear, and if we don't want to go back to kernels, basically you end up with something which is of this form. And the moment you make the assumption, which is not, obviously necessary, that this is a component-wise nonlinearity, you end up with this expression here. Okay? And this is a neural networks.
You mean this is like a one-layer network?
Yeah, it's one neural network. It's not the neural network. It's a neural network. Here and here. So here, this phi is fixed a priori, and it might depend on one parameter or two, say a degree of a polynomial. So the question is, what's the difference between this? And the answer is that here, phi is fixed in the sense that it might depend on one or two parameters, a small number of parameters, say the degree of the polynomial or the width of the Gaussian kernel or something like this. And then all the other parameters enters linearly in this expression. Okay? So the model is nonlinear, but it's parameterized in a linear way. Whereas here, the feature, you can think of this as a feature map, okay? And that's what we're going to comment next. But the overall model is not only nonlinear, but also nonlinearly parameterized. It depends nonlinearly on the parameters now. Okay? So that's the big difference from this line to this line. Okay? Does that make sense? The difference is not it's like is the really like turning point from a mathematical point of view between neural networks and everything else, because essentially the moment you have this line, you can forget about functions and you can think in terms of vectors. And basically every function is either one-to-one or almost one-to-one with vectors. So you can define inner product, orthogonality, norms in a somewhat natural way. Once you have this, if you sum up to w's, you don't get to functions. You cannot transfer the property of the space of this capital W to your functions, right? You cannot just say, I have linearity, I multiply W by a number, and then my F is multiplied by a number. You just don't have that. So in some sense, you have to, if you want to endow this space of function with nice mathematical structure, a vector space, but not only that, you want to put inner product, norms, distances. It's complicated because from a functional point of view, we lost the one trick we'll be using for a month and a half, which is basically looking at a function as if they were just vectors, okay? Again, of course you could say, well, can't I just vectorize this and concatenate with that? Sure, you can do that, okay? The point is that that vectorized matrix concatenated with the vector and the function space are not in a nice one-to-one, isomorphic relationship. You cannot just have the function space inherit that property, okay? So it's not just an accident. It's really big, That's basically why, from my perspective at least, it's one of the reasons why neural networks become really complicated to study, because all of a sudden, like analytic tools gets much more complicated. Okay? Other questions? So, yeah. Let her ask the question. Yes, here it's R to the D. No, strangely enough, I think it's correct. Because you have P rows, okay? And you multiply each one for X, okay? So this is a vector of size D, and you multiply it with P vector of size D, okay? So this should be J from 1 to P. Sorry, yes. Yeah, I changed the notation before coming inside class. Yeah, so each wj is in R D, and it's a row of yeah. Thanks. Okay. Yeah. So that was strangely correct, but more normally this was wrong. So no, that would be strange. Okay. Yes. I don't know exactly. So the question is if it's correct, if it's the correct way to think about this, that we avoided searching over the space of all possible phi's and only on some set of cognitive hypotheses. So yes, so that's what I wrote. So it basically going from, say, that line, going from this to here. Okay, we didn't write it. Maybe we can write it. So we now can write down this. Or maybe let me lazily just do this. And so yes, we definitely somewhat restrict ourselves, and I would add that we restrict ourselves to a subspace of all possible feature map, which is quite interesting because it's non-linear. Okay. Okay. So what do we want to do next? We want to, I think, make 2-3 comments. One comment is to just compare. From this perspective, there is not a lot of a mystery around neural networks, right? It's just a particular function class which happen to be parameterized both in a linear and a non-linear way. Okay. We can immediately compare it to what we've seen so far to just see a bit what's the main difference. Okay, and that's the one thing we want to do quickly because there's not a lot of complication. Then we can ask. You probably all know it, but we go over quickly about why these are called neural networks rather than linear combination of stuff, okay, that you have to learn. And then lastly, we see how perhaps this point of view of biological, we'll see the neural network come from a biological interpretation of those computations. And this is one way in which you can think of going and concatenate, use composition to create more complicated neural networks. Okay, it's one possible path among these topics. The last bit, which we're going to spend very few words about, although it could be a topic of a class, is how you solve that problem. Okay, because the short story is with gradient descent, but the longer story is that to compute the gradient, you have to do something smart. Okay, you can, or you don't have to, but you should do something smart because otherwise it takes forever. Okay, so the backprop trick is essentially a good algorithm to compute the gradient. So I think these are like the 3-4 things we can try to discuss. So let's begin with a quick comparison, which also serves as an excuse to introduce connection with a few things that were done 20 years ago. So what did we see before this? We've seen linear functions. We have seen nonlinear function with feature maps, and then we have seen kernels. Okay. A particular example of feature map was random feature maps, which was the case where we consider something very similar. I guess we call them SJs. Okay? So how do you compare this guy to each one of them? Okay, the first one is easy. That one is linear. This one is non-linear. Okay. If you compare this one to this one, Well, this is very general, doesn't have to have that specific form. If you take anything like this, the big difference, like random feature map, the big difference is that here, this is optimized, but this is chosen at random. Whereas here, this is optimized and this is optimized, okay? That's a big difference. And the same kind of thing translates to this case, okay? This is optimized, but this is not. So even this is more general in principle than just linearity plus nonlinearity, this is still fixed, okay? Let me mention in passing that this distinction become a bit blurred. So the point of view we've been taking so far is somewhat the one of, statistical learning theory, where you try to reduce to the bare minimum the number of hyperparameters that you choose by cross-validation. But there, for example, in many other approaches, people are more generous putting hyperparameters. For example, you can take a feature map and make it depend on a lot of parameters and view them as hyperparameters and do parameters from a larger space. Okay? I'm thinking, for example, take a Gaussian kernel that rather to have one sigma, has one sigma per dimension. And for example, in Bayesian approaches, this is done all the time. You do marginalized likelihood on a big set of hyperparameters of your kernel. Of course, in that sense, the distinction between this approach, again, the one where you have not only one or two, but many hyperparameters chosen by cross-validation or marginalized likelihood, and an approach like this, where you optimize over those weights, are a bit more blurred, okay? But we'll see that the big difference is going to be not that much this, but the fact that we're going to extend this by composition. Comparing to this, they look a little bit different, okay? But it turns out that this is not the only form of neural networks you can find. And for example, you can find neural networks that rather than use just an inner product, they use distances. So neural networks that look like this. Or I guess this square is not needed. So these are called radial basis function because they depend just on the radius of the distance between the point, okay? These are the corresponding neural networks are sometimes called radial RBF networks, okay? An example of sigma here could be the exponential, where I guess the exponential square, something like this. So if you take this kind of nonlinearity here, what you end up is something like look very similar to a kernel method, right? Because in both cases you can write special case would be this expression here, okay? This is a radial basis function with the Gaussian nonlinearity. Okay, the Gaussian whatever. Yeah, sometimes even called the RBF kernel. So if you now compare this line, okay, in this interpretation and this, the difference is not that the shape, but it's really the fact that the WJs here, again, are parameters, but here they're fixed to be the training set points. And this sum here can be larger or smaller than the number of training set points, whereas here is fixed to be exactly the number of training set points. If you look at the old literature, there are things like there's the old literature on splines, or where you put the knots of the spline. You can think of the xi's not just as weights or parameters, but you can think of centers. Because think of this interpretation. You're basically deciding where you want to put your Gaussians. Okay? You can put the Gaussians on the training set, but you can ask yourself, can I move the Gaussians around and find out a location which are good? And that's basically what you're doing when you take this perspective. And you can also ask, shall I take as many Gaussian as the number of points, or maybe I should take more or less, okay? And of course, the problem is that the fact that we had this result was a big deal when it came out, because it was reassuring about the fact that this was in some sense an optimal choice, that you didn't have to worry about moving the centers around, okay? And this was, in a precise sense, as good as it gets, okay? Still, you can ask if there are some other advantages to move. It shows that this is enough, okay? That you probably don't need more, but the real question is if you can use less, okay? It was a very basic result that showing that this was, So all in all, the difference are somewhat blurred, and really what the difference that stands out is that yet in all these cases, phi, k, most things are fixed, and there is just one linear parameterization, whereas here you learn more, you estimate more. Okay? Yes? Yes. The point is that, the question is, the reason why it's fixed on the left is because of the representer theorem. The reason why you don't have, maybe because you don't have a representer theorem for neural network. It's complicated in there, because assume that you ask the following question. So remember that the way the representer theorem came out was, I can choose any combination of kernels, but if my goal is to minimize the error on the data, that's the optimal one, in the sense that I know that the minimizer is in that set. So in that sense, that representer theorem holds also for neural networks. Okay, you see what I mean? So we didn't choose this. We said, let's take any combination. This is almost correct. Okay. Let's take any combination of any point. Oh wait, if I have to minimize on my data, I don't need them. I can just consider this. So in this line, you can think of it as a kernel method, but you can also think of it as an RBF network, okay? If you put here to be not infinity but p, it's going to be a bit smaller of a space, but it's still true. So in some sense, that result does say that the optimal choice in a very precise sense is choosing the weights to be the turning set points. It holds when k is a positive definite kernel, not just a nonlinearity or an RBF function, okay? So it doesn't translate to this case. But it doesn't say that that n is needed. So now the question you can ask, can I go below n? And the representer theorem doesn't prevent you to do that. Okay, so the question is still up to basically saying maybe I can use p much smaller than n. Okay, and perhaps this could be something that neural networks can do. Okay, this is not clear. So it would be not more than just proving a representer theorem. It would be proving a result that shows that you need strictly less than n in some prescribed assumption, under some well-prescribed assumptions. Okay?
With SVM, you get this and
Kind of. That's a bit of it's a bit true and it's a bit of a lie. So the comment is, what about SVM, or what if or you can also put some sparsity constraint? Yes, you definitely get less than n, okay? And that's one reason. You're still constrained to put them on the training set points, okay? So the two comments are, one, SVM in high dimension is not as sparse as one would like. Typically, you might be able to save half of the data or a fraction. It's not an order of magnitude less, okay? So P is not, the number of supervector is typically a fraction of the data points, not an order of magnitude. And the second observation is that, again, one question could be, if I allow myself to center my function out not on the training set points, can I do even less or even better than just trying to kill them? And maybe, I don't know. Okay, so supervector are still constrained to choose centers from the training set, and this one says, what if you have the freedom to do something else? Okay. All right, so this is pretty much what we can say about the comparison with other models. Of course, you could try, one question we are not going, because we are looking more at the, again, describing the model, is to try to prove theoretically that the function that you built in one way or another are substantially different, okay? That's basically the work of approximation theory. What kind of function can we describe with these models, okay? Are the function class that we describe with this model much larger than the function class we can describe with that, okay? That's kind of the question of approximation, and Tom is going to talk about these kind of results, okay? There is no learning. It's like I give you I give you a function, I give you infinite data, infinite computers. You just have to somewhat approximate the function, and you have to say which one is going to do a better job. And the goal, again, is to take the smallest possible p to do the job, okay? But we are not going in this direction today. What we do instead is we spend a few words about why are these things called neural networks, okay? Why not just RBF combination of stuff? Why networks? And again, saying stuff which is embarrassing for me because I have no idea. you can, the good thing is that you can start to draw stuff, okay? All of a sudden, instead of thinking in terms of bases, you can just do drawings. And the drawing basically is a picture to just describe the following basic operation. Okay, so it's an inner product with some nonlinearity function. So why? And the claim is that this is a basic model for a neuron. So we're going to convince ourselves quickly that this makes sense, that this, okay, it's maybe one way to think about a neuron, and then put together all this stuff and call them networks, because we do a networks of neurons, okay? So the idea here is that a neuron as a computational device has several inputs. Each one of them is a number, okay? And each of these numbers, so this is the case where x is just given by 4 numbers. And the idea here is that this computational device multiply each of these numbers by a corresponding entry, okay? Maybe let's do this. Unfortunately, here the notation is gets complicated. Again, these are numbers, and these are the entry of this vector here, okay? Oh, sorry, let me be coherent, at least in the same line. Okay, so this computational device has 4 inputs, multiply each of the inputs by a number, then sum them up. So what's done in here is just summing up wj, xj, this case 4. And then the idea is that somehow there is a transfer function in the output that basically say if the input is, well, at least in this interpretation, that is, if the input is small, I set it to 0, okay? If it's big enough, I let this input out, but if it becomes too big, I threshold it, okay? So something like this, okay? So something like this you can write as 1 plus e to the minus a, plus or minus. Is plus or minus? Remember? Minus. 1 plus e to the minus, I think so, right? Okay, so you do something like this. So essentially this says, maybe we should look at this, okay? So there is a sum hidden inside of here, okay? So there is sum j from 1 to 4, xj, wj. This is just the inner product. I just rewrote the inner product, okay? And so if you want, in this particular example, we have to write e to the minus sum xj, wj, j equal to 4. Okay? That's what it is. It's a super simple model of a neuron as a device that has a bunch of inputs, multiply them by numbers, average them, aggregate the numbers by just the sum operation, and then do somewhat a nonlinear damping of this sum before letting the number out. If it's too small or too big, it's set to 0, and otherwise you let it go. Okay? Is that okay? So next, what you can do is to say, okay, what if I want to have more than a neuron? Okay, if this is literally the function that is described by. So it's a function. A neuron is a function with d inputs and 1 output. Okay, that's what it is. So if you want, this is the f of x that corresponds to 1 neuron. Okay. Clearly, this is not very rich because it's basically just, from a mathematical point of view, just a linear function plus just teeny tiny nonlinearity. So if you want to make it a bit richer, you may want to combine more. Okay. Think, for example, what happens if, well, again, you can see it here. It's a relatively simple model. So what if you want to combine more? Okay, you can write down an equation, but you can just think in terms of this, connectionist perspective where you say, I figure out a computational device. Let's see if I can do Lego. Okay. You call it Lego. You know, you can do construction. You put them all together. Okay, and say, oh, cool. Okay, and the first thing you can do is to you combine a few. Okay, so what's the rule of the game? You have this neuron. You have this neuron. Let's say that they have the same input, just to make it simple. Okay, this one is going to have an output. This one is going to have an output. But what you want is a function. So you don't want two outputs. You have to decide what to do with these two outputs. So what do you do? It's Lego, right? So we only have one piece. So we have to use it again and again and again. But the piece we have is exactly something, which is the shape of a little ball. And you can put, 4 was not given. Well, I guess we have few pieces because we can let, at least in this game, have the output. Each neuron has as many input as we want. So it doesn't have to be 4. Okay? So that's the degrees of freedom we have. So now we can take this guy, and we send them in. Okay? Is that okay? Now this is just a number. Let's write it down. This is sigma W, let's write in the order. This is sigma sum of xj w1 j, and let me be general, j from 1 to p. This is what this neuron is doing. Okay. Sorry, this is D now. So you have D inputs, okay? And you use one neuron. So each neuron is a vector of weights, okay? Then you have another of this guy, sigma of sum j from 1 to D xj w2 j. Again, this is another vector. So w1 is in Rd. W2 is in Rd, okay? And then you have to combine them. So what do? You put a small w1 here. Oh, there are too many w's, so let's call it p. I didn't make them big enough. So let me call them b just for now. So now I have to say what this vector is doing. So what this is doing, this is taking this input, let me call it z1. It's taking this input, let's call it z2. Multiply them by a number, in this case 2, and finally give me this function of z, okay? But for me, these z1 and z2 are not just any number, are the one given by this expression here. So now we have to do beta 1, this expression, plus beta 2, this expression, and this is my f. Okay, now I can view as a function of x rather than z1 and z2. Is that okay? You can or you cannot. I think in the most common expression, in the typical way, you don't do it. Okay. The question is, shall we put another sigma here? You can. Okay. And if you want, here I'm just assuming that the last layer, the last neuron, you should, from this interpretation, you should put an extra sigma. Okay. Mathematically, typically, this is the expression that is used. But what he's saying is rightly so. You should put an extra sigma here somewhere. Okay. So we took the basic operation, which is an inner product with a nonlinearity. We call it a neuron. Then we start to combine neuron by letting the output of a neuron be input of another neuron. And then we start to going up. And we went up one. We're going to call them, when you go up, you call them layers. Okay. So we went up one layer. We went from a structure that has just inputs and outputs. We went to one that has inputs, outputs that are inputs, and then another output. So this is what you would call they're all pretty shallow for now, but at least the second one you would call it a one hidden layer network. Okay. And of course here, these numbers, the fact that I put 4 here, or the fact that I put 2 here, are just because I'm not very good at drawing, right? So this is the dimension of the input space. So this 4 should be a D, okay, which is already what I did here. And here, these 2 instead is a parameter, design parameters, is the number of units, okay, is the number of neurons you want to put in your network. And this is the P that we've been using so far, okay? So more general here, now you can think that you can now spare me the pain to do all this connecting things, okay? But here you can put P neurons, okay? W2, W3, PPP. All right, that's an interpretation. We can now think of that expression as a combination of neurons, okay? So far, so good.
So, in the spirit of learning all this factors down,
Oh, yeah. Yeah. Well, it makes sense. So the question is, does it make sense to learning for learning? Can we learn everything? And I think in general, the answer is sure. But what is the tension here? That if you can not learn it, it means that you know something about the problem and you might be able to. Usually the trade-off is you know it, you need less data. You don't know it, you need more data. That's a bit of the idea. So whenever typically you can trade knowledge for sample complex for labels, okay? So of course, when you go tabula rasa, then you have to somewhat learn everything from scratch, okay? But it's an absolutely fair question. From an algorithmic point of view, you can definitely do it. I think the next question that one should always ask is, what am I doing exactly, okay? Because hopefully what you've seen so far are models that one way or another, when you go back to this, you will have an atlas of potential algorithms where you can kind of say what are the pros and cons of different choices from a computational point of view, but also somewhat what are the underlying mathematical assumptions, forget mathematical, modeling assumption, okay? If I think the principal components are important, this is good. If I think that the principal component in some feature space are important, this is good. But if I think sparse is important, it's dead. And if I do dimensional introduction, I have to be careful because I might be already doing the same thing twice. Same thing for optimization. So I hope that when you go back to this, you just sit down and say, okay, what are the tricks I learned? And everything was just a proof of concept, right? So here, I think the big question right now is try to find the atlas of when you should do what, okay? It depends on the data, and we discussed multiple times. It's always hard to know which one, but at least if you know when it works and when it doesn't, you can get some prediction of what you see. In your next, the problem is that we're still building a good understanding on when they don't work, okay? And so it becomes a bit tricky. But from an algorithmic point of view, the question of start to parameterize the sigmas and try to parameterize more makes perfect sense. And I think at some point you're gonna find out that this is such a basic. If you look at what we did, is such a basic idea. Linearity plus pointwise nonlinearity, that even if you learn sigma, probably you're gonna at some point have to put a nonlinearity somewhere, okay? So maybe you learn this nonlinearity, but you're gonna do it. If you want it to be nonlinear, you have to put that nonlinearity as a combination of other nonlinearities. So I think this is it's a pretty reasonable primitive, okay? You can change the shape of these, you can combine them in different ways, but it's pretty primitive. In the sense, it's a pretty basic combination of computational primitives that I think it's hard to escape the moment you want to learn nonlinearities. Okay. Mm-hmm. Oh yeah, no, this is, okay, so the question is why do we do that instead of some fancier, this is just a super simple graph, why not do more complicated graphs? No, because again, up to this point, we kind of have a pretty simple graph, right? So we're just building an intuition, okay? So I think the one next thing we want to do is to say, okay, I learned how to play Lego, and let's try to do more interesting, castles, okay? This is a simple castle, and I think let's start to make it more complicated, and we're going to make it more complicated with one drawing, and then I give up and we write the equation, okay? So I think the most basic way to make it more complicated is to go up, okay? And say, well, these ones are invented, okay? The only thing which is real in this thing is what comes in here and what comes out here, because then I can compare it to the real outputs. But everything in between is an abstraction that I chose. So I chose one, can I go up and do two? Well, the rule of the game was that the moment you have 4 outputs, you put another neuron, you put them in the input of this guy, now you have 2, and then what you do, you put another one, okay? Spare me the pain to write it like this, okay? It's not too different, I just had to write a lot of stuff. But we can go back to this notation, now this is quite convenient, okay? Because essentially what you're doing is, again, you have to do the same thing which is written here, but with a z, okay, and with multiple beta. So essentially you can now, you could call this Z is a vector, how big, RP. And now you can say that you were joking. This is actually not the real function. It was just the output of the hidden units. And what you do is that you actually say, okay, we do this. We just say, this is the output of my hidden units. I let them out. It's not one number. It's p numbers. Okay? And what do? I actually do a function of z, which is, well, let's do it this way. Sigma bz. Okay? And if I want to make it scalar, I just multiply by a vector. Okay? So this is the first row of neurons. This would be the one, the column, the rows of B. Okay? This is the last layers of neurons, or the last layer of hidden neurons are the rows of B, okay? And this is the expression you have. Of course, now you can plug in this in here, and you see this compositional aspect popping out. So okay. So inside of this inside of this expression, there is a sum of neurons, combination of a bunch of neurons. And of course, now you can shout deep, and you can keep on going, right? Because it just becomes a bit annoying to write. But you can do W transpose. You can do sigma L, which is the last one. And then I do a sigma, a W2, a sigma, a W1. And then the problem is always to count the number of parentheses. 1, 2, 3. Each Wj is in R. And here we have to be careful because it's going to be in R, P, J, Pj minus 1. Okay, where P, with J is going to go from 1 to L. J minus 1, so Pj minus 1 is going to be D. So I consider now not 2, but L layers, okay? And now I have that each of I can choose the size of any of this, okay? And this is going to be some matrix. And the only restriction I have is that the very first matrix has entries that are the inputs, which, if I didn't make a mistake, is this. And then the rest is whatever you want, or just numbers, okay? So you can make a very tall, skinny network. You can make a very short, wide network. And then you can go nuts in doing something different, right? For example, who told me that every row of this has to have exactly the same inputs, okay? Maybe I can do this, okay? This guy only see these two, and this guy only see these two. So in some sense, this would be a case where the different neurons have not the same input, and even they don't have input in common, okay? So if you spend enough time with Tommy, we call these receptive fields, okay? They just have different size of inputs, and this is the case where the receptive fields, which is the set of inputs, don't overlap. If you do convolutional neural network, which I don't think we really have much time to discuss, what you do is that you allow these inputs to overlap, okay? And more than that, you put some constraints on the shape of the coefficients. Yes?
Question. Even when we do like simple linear regression, okay,
Yes.
we could be leading to like overfitting. Here we have a number of parameters that in some cases is much larger than the data. Yet I've used them and I don't they hardly ever overfit or they have very high performance. So at which point is that we have a very good generalization? Like how do we ensure that?
So that's This is a 40 million question because people have been working on this for the last 2 years, and every day there is why deep learning works. Because of statistical mechanics, because of quantum mechanics, because high energy physics, because chemistry. So every day there is a different spanning the realm of knowledge. Well, let's see what we think. Okay, so first of all, is it true that this is the first time we meet a model that has a lot of parameters? Did we work with infinite dimensional model or kernels? Did we take feature maps with, if you take in 4 dimension a degree 10 polynomial, this is the order of thousands and thousands of dimensions. So if you take a polynomial of degree 10 or 4 or 5, your dimension is 100. The number of parameters you're putting in your model is billions, okay, I guess. But maybe you can do the quick, it goes online. Anyway, so you see what I'm saying? We work with pretty big models, right? So, and what did we do up to now? First of all, we didn't stop and say, oh, we linear model. No, we just went for it, okay? And the idea was, let's go for it. Let's make it big, because we don't know what's good. So let's make it big. And then what do? You regularize, if needed, because maybe it's not needed, okay? And the whole story that we did is how you regularize. So now we can go back. How do you regularize, okay? Then you can say, well, I don't. I don't put weight constraints. Do you or not? That's the first question. When you see that they don't overfit, do you put weight constraints or not? Well, if you put weight constraints, it would be class 2, okay? Put weight constraints, and we discovered that weight constraints, which is what we call penalized ridge regression, Tikhonov of regularization, is one way to somewhat prevent, to really look inside this huge space, but only at some part. So would it be surprising that you don't overfit in the case? No. The next thing is, let's turn off. So maybe you use it without any weight constraint, okay? And then you say, oh, wait. I don't use weight constraints until it doesn't overfit. Hey, wait, but the second class after weight constraints was this one class where I jump around all excited by the idea that gradient descent, at least in simple models, is able to select not just a solution, but a simple solution. And maybe if I don't go all the way down to the end, it still performs some kind of selection of a good solution. So you're inside a huge model, but you're using optimization techniques that by itself try to find the simplest possible model compatible to your data. Okay? Then you can say, well, but I don't believe that, okay? And then the question is magic, either black or not magic, okay? Or some other tricks that you're using somewhere inside, because we've seen that even projection can do that, right? And somebody was asking, what if I put noise in my inputs, okay? What if I start to knock down entries, okay? And we didn't discuss, but for example, choosing the step size perform regularization, okay? So if you want, the way I think about these kind of things and the way I've been trying to communicating is that algorithm design is a bit more complicated than objective plus constraint. And really a set of things that they're somewhat implying that you constrain your model somehow. So I think at this point it's pretty clear that I think everybody more or less agrees that the question is not if there is a regularization mechanism or at least an implicit bias that somewhat allow neural network to search within the large space in a meaningful way. It's more a matter of proving it, okay? So again, this whole class is basically about saying, look, certain things happen in simple models. Now, you like math, go and prove it for more complicated models. But the idea that in a very large model, many things can be at work to prevent overfitting and select the right solution. If you want, before I leave and go back to drink good coffee, I think this is my take-home message. For this class, think about it in a richer way. There are many, many ways to have implicit bias. So the shorter version of the answer is I don't know. Okay, nobody really knows. But for example, Tommy has worked, and Sasha has worked, and many other people have worked to try to get good results that somewhat give some insights. And I think at this point, we might not have all the details, but I think the picture and the idea that, for example, probably gradient descent is selecting a simple solution, and maybe we're looking for the right notion of norm. I think these things, again, as you see, even just commenting on these takes 5 minutes, but I think at this point is the fact that something is at work is clear. So you want this to be the final speech when you have a trial and you give the big speech and then you go and hope you win. Okay. So, where are we? So let's, I forget anything I was saying before, so let's recap. Learning representation, not unsupervised but supervised. Linear is not a good idea, or rather not clear that it does something for you, so let's go on linear, okay? Let's compare it with other model. Essentially, you have more freedom in choosing the parameters, okay? And then we go on and think a bit what is the interpretation can give rise to the name, okay? And what you see is you can think of the basic computational unit of this model as a neuron, and then this is a collection of neurons disposed in one or possible multiple layers, okay? The jargon that comes out of this is that you want to call this hidden units, okay, and hidden layers, which are anything that is not the output or the input, okay? This function, the sigma, is typically called an activation function, which now makes sense because it's activated or not depending on the input. And this shape, which was the one which was popular, and it's kind of nice because it's smooth and so on, is, I think, more or less not used anymore in machine learning, and it's been replaced by the ReLU unit, which is what we, call like this. Is the max between A and 0, okay? So it's just it's what is called rectifier linear units in engineering. It's flat for a while. So the difference is A is not differentiable, but B is convex because it's flat and then it goes up. Of course, if you add that, then your brain might fry because when the signal that comes out is very high, you still let it out. So there could be an accumulation of high signals. Okay. At this level of our discussion until up to now, this is largely a matter of taste, okay? But I think probably both Sasha and Tommy will somewhat indicate that this function has some very nice properties, both from the point of view of the kind of function that you can synthesize with this function, and also from a computational point of view, in the sense that it is somewhat is a nonlinear function, but it has some of the properties of a linear function, particularly this one homogeneity. The property that if you multiply by a number, these things scale by a positive number, these things scale nicely with that. Somewhat a nice property that can be used in computations. I think the names are that, hidden units, hidden layers, activation function, layers. I think the jargon is more or less laid out. The last point, which again, it's complicated to draw and to write in pieces, but it's relatively easy when you allow yourself this kind of recursive nature, is this idea of going deep. So using not one layer, but multiple layers, where you somewhat do function composition. And this is another point where if just composing one layer was already complicated, composing multiple layers make life even harder. Think about it from a pure feature map point of view. What we are doing is that we are building a feature map, which is a composition of feature maps. Okay, that's what we did in that expression over there, where it so happened that each feature map phi j is equal to a nonlinearity, a corresponding wj, and x. Okay. Now, if you think about it, composition is not an operation that we use product with numbers and linear combination, maybe sometimes linear product. We don't use composition too much, and when we use it, it's typically for linear functions. Sorry, for linear function, for scalar function. And the reason is because there are not a lot of things that we know how to do with compositions. The function space that you build, of course, if you fix phi 1, phi 2, phi L. If you fix phi 1, phi 2, phi L, is just a feature map, okay? And you don't care. But if now phi 2, phi 3, phi L are parameterized and you want to learn them, it's complicated to understand what kind of space of function you're considering. For example, is it an RKHS? If you fix phi 1, phi L, yes. If you learn them, for every choice of the parameters, you have a different RKHS. So in some sense, you're working with a very large set of this specific case of RKHSs, so it's complicated to think about. One recent line of research is basically trying to show that when you do gradient descent, this doesn't change too much, okay? And in some sense, there is an underlying kernel hidden in here. In some sense, kernel are one of the useful abstraction for function space that one tend to go back to even if when you try to understand more complicated settings. We're not going to go in that direction at all. And what we want to discuss briefly is just the fact that just a couple of observations. One is that the moment you go back and try to look at the way you estimate the parameter, which are now to W1 lowercase and then WL, it was already non-convex when you have 2 and it was linear. Now it's certainly non-convex. Depending on your choice of L and sigma, it might not be differentiable. Okay, but we learn the subgradient trick. Okay, the idea that we can just replace this with the derivative of any of this function with the left derivative or something like that. So we can play that game here, and I think this is the most used idea. And so we can now do something where, if you let me concatenate everything, okay, in a vector. If you want, let's do this. Vec of WL, vec of W2, vec of W1. Okay, so let me call not B, but maybe C, the vector where I concatenated everything, okay? Then essentially the technique is let's compute the gradient of the loss function with respect to this. So let me call this whole thing f of cx. It depends on everything, okay? So what I can do is that I can do ct plus 1 equals ct minus gamma, and then I can do, let's say, I write the gradient, even though it might not be differentiable, with respect to c of yi f of c xi, okay? It would be the SGD, okay? No. So if you want here to be more precise, I do this, okay? You could replace this with the g of t, which belongs to the subgradient with respect to chi of L of yi. Sorry, this is ct plus 1, ct. Okay? So no, not even that. So this would be when they're both differentiable. When they're not differentiable, you can still define a notion of derivative that is somewhat even more general than a subgradient. Okay. So let's because we didn't introduce it, let's assume it is. So let's assume that we're using the ReLU function, so it is at least that one is convex. So everything is now is convex. So let's assume L and sigma are convex, so that at least the subgradient makes sense. Okay. So this is the basic algorithm, okay? And the basic point is that there is in computing this, you have to use the one thing you know about composition, which is the chain rule, okay? There is a special order in which you want to make the computation, and if you have a long list of composition, you also want to do it somewhat in a recursive, effective way, okay? And so turns out that the idea is somewhat old, and there are pretty nice mathematical ideas related to what is called automatic differentiation of the method of self-adjoints. And some of these ideas go back to the literature of control. And we don't really have the time or the details to essentially expand on this. But again, the basic idea here is you have to compute all the gradients, then compute the error that you obtain, and then update. And so you can view this as 2 forward and backward passes, okay? So in some sense, all I'm pointing at is the fact that in this one symbol here, there was nothing up to now. It was just a super simple operation for all the model we've seen, but actually there is a lot of interesting work to try to make that computation effective, okay? And then, of course, now you can go nuts because you can say, well, do I have to use one step size for each of the coordinates, or can I do something like coordinate descent where I use different step size? Well, you can do whatever you want. What about different layers? So, of course, at this point, the number of parameters becomes very big because you can play with the number of layers, with the number of units, with the number of step size, with the connection within the units. And if you have big computers, a lot of money to spend, you don't even have to think too much about this question. You can just do some flipper and turning the knobs and just check, okay? But what we're looking at from a theoretical point of view are essentially rules to how make, at least an educated guess to how to make these choices, okay? I think this is basically all I wanted to say. Again, what I try to express is just one view on neural network, which is neural network as a data representation. Neural network as a function class, try to highlighting what makes them a bit more complicated, but perhaps a bit more general than what we've seen so far. And then the biological interpretation, the extension to multiple layers, and just pointing, not much more than that, at the difficulty of the problem and the challenges. All right. I say if you have any questions, I can take them offline, and good luck with the rest of the course.